Hello everyone, I am Tarek Mahmud from Texas State University. Today I am here to present our paper on Android compatibility issues detection using API differences. It is a joint work between Dr. Che from Concordia University, Texas, and my advisor, Dr. Yang. Android is the most widely used mobile operating system. It is frequently updated to accommodate the new feature requests, meet new standards, or bug fixes and performance enhancement from previous versions. Android apps are developed using a software development kit, where the APIs enables app developers to use the functionalities of Android devices by interacting with services and hardware. APIs also evolved to assist developers to use the updated features in the new version of Android. The first commercial release of Android 1.0 with API level 1 was on September 23rd, 2008. Currently, we have the Android version 10 and API level 30. This shows how frequently the Android OS and API are evolving. During an API evolution, new APIs are added and some APIs are changed and removed from the older version. Android app developers have limited control on devices where their apps will run. Google recommends that developers should specify the range of the API levels their apps can support by setting min SDK version, target SDK version, and max SDK version in the Gradle file. However, developers may not verify and validate their apps on all the API levels in such range. The mismatch between the API level supported by the device where apps are installed and the API level targeted by app developers can induce compatibility issues. In the figure, we can see backward compatibility issues occur when an app runs on a device with API level that is lower than the target SDK version, and the app is using API methods that were added during API update. On the other hand, forward compatibility issues occur when an app runs on a device with an API level that is higher than the target SDK version, and the app is using API methods that were removed before that. Regardless of these two types, compatibility issues can be divided into other two types based on their usages. API invocation compatibility issues occur when an app invokes an API method that is not supported by the device. In the example code, suppose the app supports API levels 18 to 29. If the app is installed on a device with API level 21 or 22, it will crash on the invocation of this get system service method, which was introduced in API level 23. API callback compatibility issues occur when an overridden API method is in an app is missing in the API level of the device and is invoked by the underlying operating system in response to an event. In this example, the marked overridden API method was introduced in API level 19. If the app is installed on a device with API level 18 or less, it will crash on the invocation of this API method. Researchers have recently proposed several techniques for detecting API-related compatibility issues in Android apps, but existing detection techniques target only certain types of APIs or issues. For example, the CID only works on API invocation compatibility issues. The CIDR only works on API callback compatibility issues. Also, most of them use all available APIs in an API version to find compatibility issues. As we can see in the figure, the API differences are very less than all available APIs in any API version. This motivates us to use the API differences in detecting API compatibility issues. Based on this motivation, we proposed an automatic API compatibility issue detector, which we named ACID. It detects both types of API compatibility issues. Our insight is to leverage API differences to identify suspicious API methods and apply static analysis to locate the usages of these API methods in the app for compatibility issue detection. ACID leverages the API differences report to find out all changes involved in an API update. Whenever a new level of Android API is released, Google releases an API differences report summarizing the changes between two API level specifications. This API difference report consists of added, removed, and changed methods. But we only collect added, removed, and changed from final to non-final or vice versa. ACID parses the differences of all the API levels between min SDK version to max SDK version. This allows it to determine which method invocation and callbacks can potentially induce compatibility issues in each API level within the API range that is supported by the app. API differences report does not consider the differences between non-adjacent versions. So ACID accumulates all the changes compared to the target SDK version of the app to identify suspicious APIs. Not all the API differences are equally responsible for compatibility issues. We named the differences that can cause compatibility issues as suspicious APIs, as added ones cannot cause forward compatibility issues. It can only cause backward compatibility issues for both invocation and callback. So we only collect added ones from min SDK version to target SDK version. Similarly, removed one can cause forward compatibility issues for both invocation and callback usages. And we collect removed suspicious API methods from target SDK version to max SDK version. We also consider final methods, as final methods cannot be overridden. So changing an API method from final to non-final or non-final to final can induce API callback compatibility issues. Final to non-final changes can cause backward, and non-final to final changes can cause forward compatibility issues. API Usage Locator takes the app code as input and outputs all API invocation and callback usages within the app. To collect API invocation usages, it searches the API method invocations using a self-built miniature lexer and parser for Android source code. Then it applies a backward data flow analysis from API usages to extract the types of the parameters used in the method invocation and the return type of that method. To collect API callback usages, it generates class hierarchies to find if any class extended API classes and overrides any API methods. For both cases, ACID checks if the API usage is under any API level conditions or not. These are used to address the compatibility issues. API invocation compatibility issue detector uses the API invocation usages in the source code generated by API Usage Locator and the suspicious methods generated by API Difference Analyzer. API Callback Compatibility Issue Detector detects compatibility issues by checking if any overwritten API method is final or identified as suspicious by the API Difference Analyzer. Now I will discuss the evaluation of our approach. Here we tried to answer 4 research questions. In research question 1 and 2, we try to verify the accuracy of ACID in detecting both API invocation and callback issues. In research question 3, we compare the performance of ACID with the state-of-the-art techniques. In research question 4, we try to verify the real-world applicability of ACID. To answer research question 1, 2, and 3, we use 3 baseline techniques. CID is a tool for detecting API invocation compatibility issues. CIDR is a tool for detecting API callback compatibility issues. Lint is an Android Studio plugin that examines the code bases for potential bugs, including incompatible API usages. We used 20 benchmark apps from previous studies. In particular, we selected all the 7 benchmark apps that were previously used to evaluate CID and selected 13 from the 20 benchmark apps that were previously used to evaluate CIDR. To answer research question 4, we collected 35 popular open source real world apps from Google Play Store, F-Droid, and FOSS-Droid that covers 18 categories, which means it has different types of API usages. To answer research question 1, we compared ACID with CID and Lint. CIDR was not compared here as it cannot detect API invocation compatibility issues. The table shows the experimental results, where ACID detected 42 out of 43 API compatibility issues, while it reported 23 false positives. Comparing the precision, recall, and F measure, we can see that ACID outperforms the other two techniques in detecting API invocation compatibility issues. To answer research question 2, we conducted experiments on the CIDR benchmark apps and compared the results of ACID with CIDR and Lint. As CIDR is not publicly available, we were not able to run the tool, and so we used the results reported in their paper. We used the same set of apps as well as the same commits used in that paper. As shown in the table, ACID detected 36 API callback compatibility issues, while CIDR only detected 9 of them. The reason behind CIDR's underperformance is that it only considers 4 classes that were manually modeled. On the other hand, CID considers all the available APIs. This table shows the average time and memory cost of ACID, CID, and Lint. The software of CID includes the models for each API level. So the time shown in the table excludes the time cost of API lifecycle modeling phase of CID, and it is the main costly part. Lint also has the model available through Android Studio. To make a fair comparison here, we did not include the time cost of parsing the API differences reports from online. As shown in the table, the average time taken by ACID is less than that of CID and Lint. Also, CID on average used more than 1.2 GB memory to perform the analysis, as it used all the available APIs for each version. On the other hand, ACID uses only 99.8 MB memory to perform the analysis. To evaluate the practical applicability of our tool, we applied ACID to 35 popular real-world apps, such as Wikipedia, Open Camera, etc. We manually examined all the reported compatibility issues to calculate the precision score, which confirms the real-world applicability of ACID. We have recently contacted the developers of the real-world apps by emailing them or by posting issues in their public issue trackers. Some of the reported issues have been confirmed by the app developers. This shows that the app compatibility issues detected by ACID are useful in improving the software quality of Android apps. In conclusion, we presented ACID in this paper, which is a fully automated approach that detects both API invocation and callback compatibility issues. It leverages API differences and static analysis on the source code of Android apps. We evaluate the accuracy and efficiency of ACID on the benchmark apps from previous studies, which shows ACID is more accurate and efficient than the state-of-the-art techniques. We demonstrate the practical applicability of ACID by running it on 35 more real-world apps. ACID found many previously unknown compatibility issues, and some of them were confirmed by the app developers. In future, we plan to further improve ACID by integrating some dynamic analysis, and we also plan to conduct more extensive evaluation of ACID. Thank you for your attention. If you have any questions, please feel free to ask.